5 years, I've worked in a wide variety of industries, and I've probably spent the last 30 years dealing with thermal analysis. As an overview, we'll just start off. Thermal analysis is a collection of analytical techniques that measure a material's change as a function of time or temperature. These techniques are grouped together mainly historically. It's pretty arbitrarily. There are other techniques that monitor temperature effects that aren't included, and there are some of these that really probably belong someplace else. The four core techniques in thermal are differential scanning calorimetry, DSC, thermogravimetrics, TGA, thermomechanical analysis, TMA, and dynamic mechanical analysis. And we'll take a quick look at all of them in this talk. These main techniques all look at various changes as a function of temperature. DSC looks at the change in temperature as a function of temperature or in heat flow. And it gives a list of properties that are given here, melting and TG being the most common. TGA or STA look at weight loss as a function of temperature, and that's usually used to get compositional analysis or residue moisture or residue solvents. When you call it an STA, you're telling me that you've included enough sensors that you can also get a DSC signal from the material. TMA looks at changes in size and stiffness. And while that can also give you stuff like TG, the important thing for TMA is it gives you coefficient of thermal expansion, CTE. And then DMA looks at deformation and phase lag and uses that to calculate modulus and viscosity. And this is used for a whole range of things, including, again, TGA. So if you notice, all four techniques still give you TGA and melting information, which will tell you just how vital those are to many of the industries we're looking at. People who use thermal run the whole range of things, from polymers to food and ceramics, cement, aerospace, metals. There's a wide range of materials that use it. Anybody who's involved in processing a material or where their product will be exposed to different temperatures. And this can be as subtle temperature differences as what you see over a day in the summer. So how do you tell if you actually do need thermal? You or your customers have to worry about curing, photocuring, gelation, vitrification. You have problems with softening points and melting points. You're concerned about residual solvents in your material. You're required contractually to run an ISO or an ASTM method that comes from the D or E committees. Or you're concerned about one of these properties listed below, and we'll talk about many of these as we go through the rest of the slides. So we'll start off with differential scanning calorimetry. The Hitachi product line for differential scanning calorimetry includes 4 instruments, the 720, the 7000X, and then the new next to DSC 200 and 600. And we'll be doing a product introduction near the end of the month on the 2 and 600 if you're interested in more information about those. DSC looks at the change in temperature between a sample and a reference. And from this change of temperature, we can tell what's going on in the sample. It either absorbs heat or it releases heat, depending on what happens. So if we look at how to read DSC data, we see a change in the baseline here indicates a change in the heat capacity of the material and gives us a glass transition. An exothermic peak pointed up in this graph tells us of energy that's released, so for like crystallization or curing in a material. And an endothermic peak going down gives us melting or another process where energy is absorbed by the material. So as an aside, let's take a little bit of time to talk about what a glass transition is. This TG, this glass transition, is the region where an amorphous material becomes mobile. kind of like the way at melting a solid material becomes fluid. This happens the glass transition occurs over a range of temperatures though, and is often referred to by people like Mark, who are polymer physicists, as the region of the glass transition. One example of this would be cold noodles, and you can pick your type, whether they're Dan noodles or they're spaghetti. But when you think about spaghetti and how it's kind of comes out of the refrigerator as a lump, and when you warm it up, it becomes more mobile and it can move around and it's actually edible. That's a very good analogy for the glass transition. Now, when we talk about the glass transition, what most of the time we're talking about is the glass transition temperature, which is a value that is agreed upon to indicate the TG. And if we start in the bottom corner here, you can see in a heat flow curve, so the change in baseline goes up. We can take the half height, we can take the midpoint, we can take the fictic temperature, and each of these would be defined by the method we're testing to. In the TMA, we see a change in the baseline, and what's nice about the TMA is we really can see that whole region where this material changes, but we take the intersection of those two baselines as the glass transition temperature. And then in a DMA, most commonly it's the drop in the modulus or the peak of the tan delta. But if you can see by some of the other markers here, there are about 8 other methods. So it's very important when we talk about the glass transition that we know, when we talk about the glass transition temperature, that we know what method we used and what method we used to calculate it. Now, when we start looking at stuff in the DSC, we can look at a melting curve and we can see the percentage of melting that occurs in this curve. But we can see that if we melt chocolate, we get 2 separate peaks. And chocolate is an interesting material to study in the DSC because the properties that we look for, that melt in the mouth silkiness, is all a function of the cooling cycle and when you reheat it where the melting peak is. So good chocolate tends to melt at about 28 C. Really cheap chocolate can melt at a lot of other temperatures depending on how it was made and how the processing was. If we look at materials that cure, and to the DSC, whether we cure by light or whether we cure by heat, turns out to give us very similar data. If we look at irradiation curing, because a lot of people are moving to optical curing methods where we irradiate because you get less VOCs, so you have less pollution, we can see that as intensity increases, the energy of the cure increases. And then if we were to reheat the material, we can see unirradiated material gives us a very big energy of curing. And as we increase it, it gets lower and lower. And then when we're using really high wattage, we see nothing, and we just see the melting of the material itself. So DSC lets us study this in the instrument so that we can model our processes pretty exactly. In pharmaceuticals, there's a lot of applications for DSC. We can look at protein denatation. We can look at freeze drying or lyophilization of drugs and vaccines, which is a really important one now. We can look at storage temperatures. We can look at polymorphic forms. When you take a drug or you take a medicine, there are often various crystalline forms that you can have, and only some of them are biologically active. So if your drug doesn't have the right polymorphic form, it may not work right, or it may work too well. And the only ways you can detect polymorphic forms are DSC and X-ray crystallography. We can look at percent crystallinity or amorphous content. They're kind of the inversion of each other, kinetics and compatibility studies. And this here is actually looking at various forms of a polymorphic drug at different heating rates. And we have form 1, and we heat above that, and it converts to form 3. We look at straight form 3, we get that. And then we can look at what's called a pseudopolymorph, where we have a dehydration of water that occurs, and then we end up in form 3, which is the thermally stable form. Now, one thing that's often forgotten is that DSC, because it looks at melting behavior, can actually be used to estimate purity, and it can estimate purity at very high levels. So if we look at these curves here, we have 100%, actually 99.29s, pure painkiller, and then we have 99.3, and you can see how it's broadening. The peak and the slope of this line is changing, and then we have one at 98. So by looking at the change of the slope of this line, we can estimate the purity if we know the molecular weight. Now, there are a few limitations on it, and so it's a little bit more complicated than this, but for materials where it works, a 20-minute run will give us a purity to two decimal places. So it's a very, very quick way to measure the purity of APIs. Another application is kind of on the other end, is polymer recycling. When we look at polymers, a lot of them can be sorted by just IR, but two classes of recycled polymers are different types of polyethylenes, and the IRs are very, very similar. So what we can do is look at these in DSC, and in DSC, very, very quickly, we see the differences between low molecular, linear, low density, medium density, high density. The peaks come out very similar. If they're blended together, there are actually programs available that we have where we can separate them into peaks so that you can estimate how much is that. And then just for detection picking up, the detection limit in IR is about 1% off of a solid pellet. In the DSC, we can go to with sensitivity, we can go to very low concentrations and pick up that these two peaks here have just a little bit of polypropylene in them, which could cause problems as you try to use the recycled material. Modulated temperature DSC. DSC can be oscillated so that the heat flow varies as a function of time while we're heating up at a set rate. So we basically have two heating cycles. We have a sine wave that's imposed over a ramp. When we do that, we get a curve that looks like this green curve up here. The average of it is our total heat flow. However, because this is a sinusoidal wave, we can break it into an in and an out phase component. And from that, we can get a reversing heat flow, which gives us thermodynamic behavior like the glass transition, and non-reversing flow, which gives us stuff like curing and cold crystallization. So that we can actually take a peak like this one down here, where there's an endothermic peak where we expected our glass transition, run the same experiment in an oscillatory mode, and then we can actually pull out in the reversing, the TG that's buried in here, and we can pull out the energy of the cure and get them both in one run. So it can clean up dirty glass transitions. It can take away the loss of water from a transition. So there's a lot of applications of this technique. Now, that kind of is a very quick summary of DSC. So what we'll move to next is TGA. And we're doing them in this order because DSC is probably the most common technique. It's probably 70% of the people using thermal out there are using that, where easily, maybe another 20% are using TGA. So these are the two big techniques that most people are familiar with. And we offer the Nexta, and it is shown here with the auto sampler and the real view system attached inside the protective hood that keeps your fingers from getting caught by anything. And you can see here on the screen, we show, not only do we show the weight loss curves, but we show the images that would come from the real view system. And we'll talk about real view a little bit later. Thermogravimetry is basically weighing a sample in an oven. We heat the sample up at a set weight and we watch the weight change. And as we're doing this in an STA, we also monitor the heat flow. The compositions can be used to tell us what's going on in the thing. So we get an initial loss in a tire rubber, and that's solvent loss that's on the surface of the material. And we're running a dry gas over it, so any water that comes off. Then when we heat it up, we lose the oil that's added as an extender. At higher temperatures, the rubber burns, and that's usually a two-part burn like this. And then we'll come to another plateau. And at that plateau, we normally switch to oxygen. And above that, we have carbon burning off. First is amorphous carbon, and second is crystalline carbon. So that would be graphite in most cases, but diamonds actually burn here too, if anybody really wanted to know. And if there's any metal in this, after we burn it off under oxygen, we're actually going to see a weight gain as the metal oxidizes. So this is probably the most common use of TGA, and most of this is done by previous knowledge. It's not a absolute basic technique where it would give you numbers without knowing anything about the material. So why do we use STAs instead of just a straight TGA? Well, the continual problem with TGA is the stuff comes off and we're guessing. And so a lot of modern regulations want to know that. We also can't see things that don't have a weight loss. So here, all of this stuff, the glass transition, the cold crystallization, and the melt happen in a part of the TGA that gives us no information whatsoever. And then the final reason why we would want to use an STA rather than a TGA is calibration. There are no traceable absolute TGA standards. They're called Curie point standards, and they're just not commercially available. However, there are lots of melting point standards. So the STA allows us to calibrate and to calibrate with traceable standards, it's a big point for a lot of industries. When we look at the TG DSC, and as you noticed, there's several names that are on the top of the slides. It can be called an STA, it can be called a TG DTA, it can be called a TGA DSC. Depends on basically when the people were talking, the name kind of changes with time. But we can look at things like a thermal decomposition, and we'll see a weight loss, and we'll see a peak in the DTA. And we can go down, and with the two of these, we can sort out things that would normally be different, because thermal decomposition and oxidative decomposition are going to give you the same kind of TGA curve, but they give you different DTA curves. And similarly with melting, crystallization, glass transition, sublimation, these things, dehydration, these things all give curves where this thing can sometimes help you sort out what's going on. So that makes the combined thing much more useful when you're trying to figure out what your material is actually doing. Now, I mentioned that you need Curie standards to calibrate that, and that's actually a fairly important test in people working with chips and electronic heaters and Peltier devices. Is the Curie point is where a material loses magnetism. And above the Curie point, iron, for example, is no longer magnetic. And that happens about 770 degrees. Nickel happens about 360, and it's the same thing. So any magnetic material is going to have a point at which it loses magnetism. And a lot of design characterizations in materials require knowing this. And you can use it because it is a sharp transition to calibrate a TGA by putting a magnet under it and watching the change in weight. However, as I said, the problem is there aren't really traceable standards, and there are pretty much only two elemental standards between 0 and 1,000, and that's iron and nickel. Oops. Sneak preview. One way to improve your accuracy even more is to hook a mass spec up to the back of it. This is an example of our next to STA hooked to a to an Extrel mass spec, and that allows us to do things like look at the weight loss from this. This is actually a vaporing solution that has a certain amount of nicotine in it, and we can, if we can take one point in this curve, we can see what the mass spec looks at that point, and and be sure of exactly what's coming off at that particular temperature. So that's another way to improve the accuracy of your system. The more common way, what most people do, is they look at comparisons. So we have polyester, cotton, and then we have the blends in the middle. And as the concentration of the blended yarn will change, the curves will change, and you can estimate from that. The other way to improve your understanding of what happens to your material is using the real view system. And you can see we have in the lower right, we have a new rubber and a used rubber, degraded rubber, and we can see there's a very definite difference in the TGA, but there's also a difference in what happens to the material visually. You can see we have a lot more flow in this material than we do in this, which is kind of standard because rubbers, as they degrade, tend to cross-link and get harder. Another commonly used test is to look at oil that's used in compressors and motors and that. And there's a test called the NOAC test, which requires putting a sample of oil in the oven for an hour and letting what happens and then weighing it. You can do the same thing in the TGA. You can put it in, you run a standard oil to know what your temperature is, your target temperature is, and then you can use the oil to pick these out. It's faster, and the nice thing is it requires no time from a technician to actually have to take care of it. And finally, in the software, and as we get into the software, there is the problem that exists is if we run things slower, we get better resolution, but the runs take longer. If we run them faster, we get data faster, but we may not get as good resolution. So one way to address this is controlled rate analysis. And what we do there is we basically watch the derivative. When we hit to a point, we change our heating rate. We get to a stop point, we put our derivative back. And the way this looks in real life, if we do a run at 10 degrees a minute, we get curves that look like this. If we tell it every time it loses weight to go to 1 degree a minute, we can make the curve look really, really sharp. Now it takes longer than the dotted curve to do the solid curve, but it doesn't take anywhere near as long as it would take if we ran the entire experiment at 1 degree a minute instead of 10. The other big software component that people using TGA use is kinetics. And what that does is we take a bunch of curves, and this is polystyrene run at various temperatures to watch it degrade. We calculate an activation energy, and from that we can do a lifetime prediction and say what is going to happen to the material at 350 degrees or at 250 degrees, and how long is it going to stay before it starts to fail. And it's a fairly straightforward method. There's actually an ASTM method for it, and it gives you data very, very quickly compared to what running all of these as lifetime experiments would be. Because if you look at our scale down here, we're looking at the log of days. So these last data points out here are on the order of years. Also, the same software lets you model what would happen if you run at different rates. So if you usually run everything in your lab at 2 degrees and somebody sends in data at 0.1, you can actually convert it and get an idea of whether or not that data would match yours. The other thing that STAs let us do is they act as a high temperature DSC. Most DSCs stop working at 700 degrees or so because their electronics and their sensors are designed that way. The STAs allow you to collect data up into 1500 degrees. Here's an example of it. We have the Curie point of iron. We have the transition of ferrite to austenite iron. And then we have the transition back to delta ferrite. And what we would want to do is get up to here if we were making something in metal and then crash cool it to trap it so that we had hardness. But this lets us see the exact position of these peaks because they vary with the alloys and the additives that you put into the steel off of iron. It also lets you get just melting points of materials like silver or ceramics that melt above 700 degrees. And you can get heat capacity data from this too. Alrighty, the third technique, and now we're starting to talk about techniques that are about 10 to 15% of the marketplace, is thermogravimetric analysis, thermomechanical analysis. And here is a TMA 700 showing the expansion curve for steel heated from room temperature, where it's gray, up to about, I think this was 900 C to get this nice red color. And for steel, that gives us a straight line. So what basically thermomechanical analysis is measuring the size with a very accurate micrometer, normally an LVDT, as a material as it heats up. One interesting effect of this approach is that the TMA is more sensitive to the glass transition than the DSC, so a lot of people will use it for that. But the real important thing is it's good for measuring thermal expansion. And an example of thermal expansion is, here's a bottle of wine that was made and bottled at about 20 degrees C. And here's the same bottle after sitting out in somebody's backyard at 40 degrees C in the Texas summer. And you can see how the expansion of the liquid has compressed the air in it, and it's actually starting to push the cap out. And so, a very visual effect of what thermal expansion means and what the problem is. Now, when you start dealing with the bulk samples like this, we have to take into effect geometry. So we do have the ability to do expansion and tension. We also have the ability to do penetration and bending. These tests give you something called a softening temperature, and they're older methods, so people like to be able to occasionally duplicate them to compare modern stuff to techniques that were done before people really knew what a glass transition were. So that you can get various geometries into the TMA and use those depending on what you need to measure. When you read TMA data, what you get depends on what kind of test you're doing. If you're doing a expansion test or in either solid or tension, you get a curve where you get an expansion of the material, the CTE as a function of temperature, you get the glass transition region, and then you go into another expansion. For penetration and flexure methods, you get a curve that may or may not have a little bit of line of slope to it, and then at some point the curve drops as the material penetrates or folds. Here's an example of CTE on some glass. This is a glass standard. You notice we have a very, very flat line of expansion. We get to the glass transition region, the curve turns, we calculate the TG, and then at some point it starts to drop. And at this point, the weight of the probe is applying enough force to the material that it flows and it starts to squish out from under the curve. We can also, in extension, look for the glass CTE and the glass transition. This is especially important in things like films and fibers. But in fibers, if we continue going up, we'll actually see a change. And that change is called the heat set, and it's where you induce hand or texture into a fiber or something by twisting it. And this becomes very important in the fabric industry because dyeing is done in the region between the end of the glass transition and the start of the heat set. When we go into looking at films that have been pulled as they were made, so they're orientated, we see very different curves looking at the in the longitudinal or the machine direction versus the transverse or the cross machine direction. So we get very different curves in expansion or extension as we look at the film, whether it's lengthwise or crosswise. Now, certain samples are irregular, or sometimes you just want to get the volumetric expansion, and the material can be irregular because it's a broken piece, or it can be irregular because it's got fibers or packing in it that has an orientation. And then we can use a volumetric expansion approach. We can do silicone powder, we can put an oil in here, and put a liquid in here, we put a top on it and drop the probe on the top. And then from that, we can get a volumetric expansion. And then we just have to divide by 3 to get the linear expansion. So here we are measuring the volumetric expansion of a piece of material buried in aluminum oxide. And in that case, I would measure my aluminum oxide expansion first and subtract it. Okay. So one of the other things we can do is mimic old tests. If you are working with, data that goes back, 50, 60, 100 years, like a lot of people in the polymer industry do, some of your data uses a penetration test for softening point or a flexure test. And you can do that here. And you get numbers that are very similar to the glass transition, but you do it by penetrating the material with a probe and seeing how quickly the material softens enough that the probe under a certain load can get done. One advantage of that even today is if you have a wire with enamel on it or a coating over a metal surface, a penetration test will allow you to actually measure that material on the surface by penetrating down against the base material, so that you can actually test something without having to scrape the coating off the wire or the film off the disc or whatever. You can also, in the TMA, do creep recovery and other static tests. And most TMAs these days have the ability to do a little bit of dynamic testing, usually over a very limited frequency range and not as well as a true DMA. But if you need one test a year, it will do it for you. So our last thermal technique and our second to last topic is dynamic mechanical analysis. Here's a DMA. And if you notice here, there's like a little window, and this is for the real view system, which we'll talk briefly about next. And what the DMA is going to give us is a storage modulus, a loss modulus, and a tan delta, which are on this. So with the DMA, what we do is we apply a force to cause a deformation, and we look at the difference between what's applied and what the material responds. That gives us what's called a phase lag, and then we look at the deformation at peak. And from those, we do all of our calculations. We can also plot these as force versus deformation in a Lisa loop plot, which is shown down in the bottom, and that lets us look at how the material responds on cycles and gives us a property called hysteresis. Now, when we divide that sinusoidal signal into 2 parts, we get the in phase, the storage modulus, the energy we get back elastically. We get an out of phase, the loss modulus, which is the energy lost to friction and internal rearrangements. And then we get the ratio of the 2, which is kind of how good the material is at dissipating energy and is sometimes called in the older literature damping. How we read one, this modulus can be thought of as similar to Young's modulus, and it tells us how stiff the material is at a set temperature. The loss modulus tells us how the material is going to dissipate energy viscously, and then the tan delta tells us about the damping. And this is actually studied a lot for people doing acoustics and vibration studies because it allows us to look at how well the material dissipates energy, and the best point for this stuff would be here at the peak. An idealized DMA scan is shown here, and I'm not going to spend a lot of time over this slide. I will slip in an advertisement. This comes out of my book on dynamic mechanical analysis, and we spend chapters discussing all the stuff going on here. But the important point is if we start at high temperature melting and we go down, we get the rubbery plateau and the glass transition, but then we pick up these other transitions that are not visible by other techniques. And some of them are important, like beta transitions are related to the toughness of the material in the solid state. The plateau here is related to the crosslinks or entanglements between the chains, and hence gives us an idea of crosslink density. And you can see there's some other things that appear in semicrystals and crystal slips and very crystalline materials. So there's a lot of stuff that you can pull out of a DMA curve that you can't see by any other curve. And this is one of those things, if you have any questions, please give me a call later, because it's, like I said, there's almost a semester of graduate work here. DMA's dirty secret. 85% of it is used only for the TG. It is estimated to be 100 times more sensitive to the presence of the glass transition than DSC is. And if we look, we can look here, we can see a drop indicating the glass transition at the top, the peak in the tan delta, which is another indication, the peak in the tan delta down here, which is another indication, and then a peak in the loss modulus. And all three of these have been used in various industries for indicators of the glass transition. If you notice, they don't line up exactly right. And that was one of the reasons why it's important to remember that the glass transition is a region of behavior. It is not a specific temperature. Here's an example run on a cured material. The DSC curve is shown here. No post-cure, we get a nice TG. An hour of post-cure, you can't see it anymore. You go and look at this in the tan delta. There is no post-cure, an hour of post-cure. And there's 2 to 8 hours of post-cure. So 8 hours after it vanishes from the DSC, I can still see that glass transition in the DMA, which is one of the real advantages for highly cross-linked or highly filled materials, that the DMA will see transitions that are very, very weak. Those other transitions, as I said, can be important. You know, if I look at a nylon that has enough toughness so that it doesn't break in use as a computer connector, I get one curve. If I look at the stuff that's failing, the temperatures are about the same, but the beta transition is much weaker here, indicating that the material has much less ability to disperse and dispel energy and impact in the solid state. And here is just another example showing very low temperature transitions working all the way up to the TG. And we're starting to go into the cold crystallization there. So you can get a lot of information on these lower order transitions. You can detect because it's so sensitive, you can use it to detect differences in crystalline and amorphous behavior. And sometimes that's subtle, partial melting in that, in a crystalline film. And an amorphous film, it can be pretty exaggerated. In PET and in silicone rubbers, after you go through the glass transition, the material can rearrange and you can get an actual increase in modulus where the material forms more crystals in the run. And while you can pick this up in the DSC, you can only pick up the temperature change. You can't see what kind of change this makes in your modulus behavior. And in PAT, it doesn't make that big a difference, but some of the silicone rubbers are actually stronger after the cold crystallization than they were before. Okay, damping. Damping is the ability, the tan delta, the ability to dissipate energy. And if you can see here in two different materials, you get very different effects in a material. And if we are working up here in the rubbery range on both of these, this material is going to be much better at being a rubber than this one is, where the peak isn't as strong, isn't as localized. So there's a lot you can pull out on material properties from the tan delta curve too. Now, if you notice in a lot of these, we're showing multiple frequencies, and that's because the glass transition has a dependence on frequency built into it because it's on Arrhenius transition and it's time dependent. So as we increase the frequency, we can increase the apparent glass transition temperature, usually by somewhere between 5 to 15 degrees per decade. This can become real important if you're designing something and you're testing it at 1 hertz and it's going to be used at 10,000 hertz. Another technique we can do with this is, once we have frequency data, is we can rearrange the curves so that they're against frequency and then move them around and add them together in what's called a time temperature superposition. And when we do that, here's where we measured the material, and here's the range that the time temperature superposition gives us. So it's a lot bigger. It lets us look at a lot greater range. And there are several ways this data can be collected, including our synthetic oscillation mode, which really speeds up the collection of the data. Now, a couple of times I've talked about the real view system. The real view is an accessory that can be added to our instruments that allows you to monitor the sample real time. So if we take a look at a sample in the STA, we can actually look as we go up in temperature how the material changes. We have a camera focused on it, and we can just watch as we go from a solid to a melt that's starting to burn, and to pretty much a char up at the top. And then all of these can be tied to temperature in the material. We can also, and this is something that I find really cool because I'm partially colorblind, we can also look at color analysis, which when you're say you're looking for the start of oxidation in material where it begins to turn yellow, well, operators are going to see that at different times. And in the series of data on the bottom, my boss can pick it up a whole lot faster than I can. We can actually use the color analysis to tell us where the yellow is increasing and how that's happening. A more striking example is a color-sensitive paper that as we heat the material up and we run, we can actually see the color change. So it allows us to see changes in the material visually, which gives us a little bit Siri. One place it's becoming quite popular is academics. We've sold these to a couple of teaching labs where the university is going to have students running DMA or DSC and being able to watch the sample so that they can actually understand what is being done by the sample. All righty, that finishes the talk. I am open for questions, or if you just want to email me, you can send them to Hitachi-hitech.com, which is my name. All righty, thank you.